This video will demonstrate some of the properties of ammonium nitrate under stress and show the behavior of ammonium nitrate when exposed to fire. Since the earliest days, explosives for mining and quarrying had to be handled under the most stringent of explosive regulations. The continuous development of ammonium nitrate technology, coupled to the development of truck-mounted explosives mixing and loading machinery, has resulted in significantly advanced safety and performance. Today, the majority of Orica products are made from non-explosive chemicals mixed on-site in mobile manufacturing units. Ammonium nitrate is the main component of these modern bulk explosives. One of the main potential chemical hazards associated with ammonium nitrate is its ability to intensify a fire in combination with combustible materials. What we will do is conduct a series of laboratory demonstrations to highlight the effects. But first, let's go back to the basics of fire itself. Fire generally requires three basic elements: fuel, for instance timber or cloth; oxygen, either from the air or from a chemical substance; and of course some form of heat to produce ignition. Ammonium nitrate itself contains chemically bound oxygen, which in the right circumstances can be released. In other words, it's a powerful oxidizing substance, and given enough heat, it can help materials to burn even in the absence of air. Our demonstrations also draw attention to the potential of hot ammonium nitrate solutions to react with organic materials spontaneously, particularly on manufacturing plants. In practice and in transport situations, this is most likely to occur when hot residues from, say, an ammonium nitrate vehicle fire become mixed with dry organic materials. Our demonstrations will look at the oxidizing properties of ammonium nitrate and how it can strongly support combustion. Firstly, let's examine the behavior of ammonium nitrate when heat is applied. As we can see, it begins to melt. However, it does not burn. Even though substantial heat is applied, the ammonium nitrate merely melts. If the heat is sustained, the ammonium nitrate begins to fume as it decomposes. But still, it does not burn. Here we see how a pile of plain sawdust behaves when the gas flame is applied to it. The sawdust ignites quite readily, and the whole combustion spreads quickly over the total surface of the pile. But just as quickly, the combustion appears to die down. Opening up the pile shows that the sawdust is burned mainly on the surface. This is because there's not enough oxygen to support combustion inside the center of the pile. Once a fresh surface is opened up and exposed to air, the combustion begins again, simply because more oxygen has become available. The previous demonstration is conducted again, but this time the pile contains a mixture of ammonium nitrate and sawdust. As you can see, the mixture ignites rapidly and burns quite vigorously. This time, it is clear that the mixture is burning completely, even deep in the center of the pile. it has been completely burned out, because this time the oxygen necessary for combustion was provided by the ammonium nitrate contained throughout the mixture. This demonstration will show that ammonium nitrate can support combustion even in the absence of air. Again, the pile is a mixture of sawdust and ammonium nitrate, but after ignition it is covered with a funnel to exclude the air. The fumes we see contain oxides of nitrogen and other gases released by the burning mixture. It is important to note that these are toxic gases. Upon examination, it is clear that the pile has burnt completely again, even though the oxygen was excluded. The ammonium nitrate has supplied the extra oxygen necessary for total combustion. Now, let's see what happens to a piece of cloth which comes into contact with a hot, concentrated solution of ammonium nitrate. At first, it reacts with the cloth, giving off fumes. The reaction intensifies and more fumes are given off. Soon, there is enough heat being generated for the cloth to burst into flames. Notice, no extra source of ignition was required to start the fire. It is simply caused by the hot, concentrated ammonium nitrate solution. This is in fact the standard reaction between a hot, concentrated solution of ammonium nitrate and a combustible material. In this example, a similar reaction occurs with tissue paper. First the fumes, and then sufficient heat is generated to start the tissue paper burning. You'll notice this tends to be quicker with the paper than it is with the cloth. The spontaneous combustion effects we have just illustrated were achieved with solution temperatures and concentrations substantially higher than those used for transport and storage of ammonium nitrate. In summary, what these demonstrations show is, by itself, ammonium nitrate does not burn. However, it does support combustion and will intensify fire by releasing oxygen. Exclusion of air does not stop a fire involving ammonium nitrate. Therefore, chemical extinguishers, foam and CO2 are ineffective. Water is in fact the most effective agent for fighting fires involving ammonium nitrate because it absorbs heat. Water dissolves the ammonium nitrate and slows down the oxygen-releasing chemical reaction. As we said at the beginning of this video, ammonium nitrate is a significant advance in safe explosives technology, provided its properties are understood and it's handled correctly. Orica hope you now have a better understanding of some of the properties of ammonium nitrate, helping you maintain a safer working environment. Orica Explosives, providing results with safety.